Lights on. Lights off. Now what can you see? Nothing, right? Light helps us see the colors all around us. Well, visible light, which is red, orange, yellow, green, blue, indigo, and violet. But of course, we can't see the entire electromagnetic spectrum with our own eyes. Now look at this. I'm cooking cookies in the oven, but come closer. The color of this oven. Do you think it's red, orange, or even yellow? How about the colors we can see? The ones from infrared radiation. Now an oven can be an example of a sort of blackbody. Now blackbodies are perfect at emitting and absorbing radiation. That can include the sun, the stars, or even an oven. Now ovens aren't exactly blackbodies, but they come close to our purposes. Because all objects emit electromagnetic radiation, even you, they will cool to the surroundings in the form of radiative cooling. So we can't have any objects that have the possibility of reflecting any colors in our experiment. Take this oven then. When the temperature increases, the color inside starts to glow this bright red, even white. What we see here confused many people in relation to the Rayleigh-Jean's law. In their experiment, they said that as the temperature went up, the color of the blackbody shifts from this red to this blue-like color. But mathematically, in the Rayleigh-Jean law, this did not count for this color shift. They devised that the spectrum of light will follow the equation of energy density is equal to 8 pi v squared times k times t over c squared, where v is the frequency, k is Boltzmann's constant, t is the absolute temperature of the radiating body, and c is the speed of light in a vacuum. Which means that as the temperature went up, the line of the graph exponentially increased, which indicated a red color. They saw this and they were definitely stumped. We call this the ultraviolet catastrophe. It is not until Max Planck devised the idea that energy was actually quantized. Quantized meaning discrete packets. Energy can be gained or lost in these quantums by integral multiples in these very small units of energy. So we actually believe there was a curve, where there is a peak intensity in relation to the temperature that allowed the color being emitted as such. There's a sharp decrease in intensity at shorter wavelengths, usually at the ultraviolet region, and that's why we see the shift in color in the oven. Not only is that color seen, but we also get infrared radiation, which we can't see. Prior to this, people thought that energy was continuous, which made sense to the human eye. Thus, Planck made a constant, which was 6.626 times 10 to the negative 34 joule seconds. He created this formula to describe the energy in the light all around us. E equals nhv, where E is the energy, N is the integer, the number of photons, H is Planck's constant, and V is the frequency. The integer meaning that we cannot have energy exist not unless at these whole values. Thus, the integer followed suit of the quantization of light, where the objects you see have their specific color due to the atom jumping from one energy level to another. As they jump levels, they emit light in accordance to the magnitude of the jump. And that's how we see the distinct colors all around us. Maybe next time that you bake those cookies, you think about the blackbody radiation that led to the idea of the quantization of light that made those delicious cookies.